Well, good evening, good evening, Copernic friends and family. Uh, Great to have you here this evening. My name is Drew Desker. I'm the director of Copernic Observatory, and really excited about this evening's live stream program. Again, we really wish we could have people up here, and I'm hoping if the numbers start continue in the path that they're going, we'll hopefully sometime this summer be able to start doing our in-person programs up here. And unfortunately, tonight, of course, it's just teasing me. It's an absolutely clear sky tonight. But anyway, I just want to make you aware of a couple of things that are coming down the road. Again, we'll continue to be doing some live streams. Next week is actually Victor Lamoureux, who's a SUNY Broome professor. We'll be talking about trail cams and what we can learn about nature through those trail cams. We'll have a talk on cicadas. Brood X is coming up this spring, and so we'll have a talk about that. We'll do a talk about the Skywarn recognition. There'll be a Skywarn training from a gentleman from the National Weather Service. So a bunch of good live streams coming up. Also, for those of you who are here in the area, you'd know that every June we would do a rocket fest where families come up and build those little Estes rockets and then have them launched from here. We weren't able to do it last year for obvious reasons, but this year we're pressing forward, and we're going to do it in a bit of a hybrid fashion. In that, if you sign up for a Rocket on Rocket Fest, you can go to our website for that. Then what you'll end up doing is building it at home. But then, if you've got any questions, subsequent weekends we're going to have some Zoom consultation sessions so that you can hold up what you got, or you can ask your question. We can help you out that way. And then there will be launch windows where you can come on May 22nd to launch your rocket. We'll check it out, make sure everything's running, looks right. Then we'll put the engine, the wadding, the parachute in, and let you launch it. So go to our website for Rocket Fest. And also, we're very excited to be offering in-person summer camps again. We're doing that. We weren't able to do it last year. We had to do everything virtually last year. But this year, we are going to do in-person summer camps with a limited number of students in the class, so we're making it safe. But we're also doing some offering virtual camps as well. I'm going to wrap back around into the live stream briefly. One of the other, our live stream astronomer, Jerry McCarty, has been working on a Lego version of the Space Shuttle and the Hubble telescope. And I guess coming up on April 25th, I believe, is the 30th anniversary of Hubble being put into service. So he actually has a time lapse of him building that, and so check out our YouTube stream, because he'll post that up on I believe on April 25th, and Jeremy will tell you more about that next week as well. So here we are. It's interesting how I came to sort of connect here with Daniel. I saw on the local TV station very soon after Perseverance had landed, the local news station did a story, and Daniel was featured on it. And so I did a little snooping, and was able to ultimately, through his parents, track him down, and come to find out, Daniel, again, grew up here, and he'll tell you about his experiences at Copernic as well. So, Daniel, we're going to turn it over to you. Thanks again for doing this, Daniel Krysak from MAHLI and Space Science. Well, I'll let you introduce yourself.
All right. Well, thank you very much, Drew. I appreciate you all having me here. So as Drew said, my name is Daniel Krysak. I am an Endicott native, actually. I actually work for a company now called MAHLI and Space Science Systems out here in San Diego, California. Specifically, our company specializes in building space cameras. We have a number of cameras on various spacecraft. We've got quite a lot of cameras actually on various spacecraft around Mars. We have a camera on a spacecraft at Jupiter, another one on the Lunar Reconnaissance Orbiter around the Moon, and a handful of others. So we're all over the solar system, if you will. I specifically work on the Mars Curiosity rover, the 2020 Perseverance rover, both on Mars, and then also the Juno spacecraft that's currently around Jupiter. Been doing this now for actually a little over 9 years. Back in early 2012, I started. Give you a little bit of a quick background about myself here. So as I said, I grew up in the Endicott area. My interest in the space sciences kind of came about really at a young age. I'd always go out with my parents, looking at the telescopes at night. Did numerous events at Copernic throughout the years. I couldn't even tell you how many I've gone to. We did pretty much any of the summer events. We would always be at least a handful of them. Always looking through the telescopes, doing whatever. I actually volunteered even at Copernic back in early 2009 time period. It's a lot of fun. Great place. So shameless plug right there to Copernic. So after that, I went on to get my graduate degree. My degree specifically is in geology, and very specifically, I have a master's in planetary volcanology. I got it from the University of Buffalo. For my degree, I studied a volcano on Mars named Apollinaris Mons, and I basically remapped the geologic history of the volcano. At the time, it had only been studied in the early 90s, just with the only data available really to us at the time, the Viking orbiter data. So by late 2000s there, I when I was starting my grad degree, we had a lot more high resolution data now. In particular, I used the Themis cameras that were on the Mars, or that are on the Mars Odyssey orbiter, as well as the CTX camera that's on the Mars Reconnaissance orbiter, which in the end, coincidentally enough, were cameras that my company that I now work for built. I did not know that at the time in grad school, but so I remapped the geologic history of the volcano, made a couple interesting new discoveries that we couldn't even tell with the Viking orbiter data. So that was really interesting. And right after that, I saw that the company, MAHLI Space Science Systems, they're looking to hire. Unfortunately, my graduate advisor actually knew some of the company, so I got in touch with them, and they hired me about 6 months before MSL Curiosity Rover landed. So with that, let's jump into the presentation here. Let me start sharing my screen. Okay, so as I said, we'll be talking about the Curiosity rover itself and the cameras, the 2020 Perseverance rover, and then the JunoCam instrument after that. So specifically, the cameras that my company built are the two Mastcams. They're located right on the top of the mast. We have both a 100 millimeter and a 34 millimeter camera. We'll get into the differences of those in a little bit. We then have the MAHLI instrument that is mounted on the end of the arm. That stands specifically for the Mars hand lens imager. Idea behind this is the same thing as a geologist hand lens that they use to see a rock up close. And then lastly, we have the MARDI instrument, which stands for the Mars Descent Imager. Now, you can't really see in the image too well because it's actually mounted on the undercarriage of the rover, pointed down. So we'll start with MARDI first. Now, the reason why we'd have a camera that is pointed like that on spacecraft is because when Curiosity back in 2012 was going to land, there was a new landing system on it. The previous rovers all landed with the airbag system, and Curiosity, being so much larger, was not able to use that. It would have actually popped those airbags almost immediately. So developers up at NASA's Jet Propulsion Lab, JPL, they devised a new landing system that involves what they call the sky crane. So part of this landing system is as the spacecraft is coming through the atmosphere to land, and then the heat shield deploys. At that point, the bottom of the rover is completely open and exposed to the atmosphere. Now we're still, tens of kilometers up in the sky at this point. So the idea with the MARDI camera was to mount it, on the undercarriage of the rover, point it down so that when the heat shield separated, we'd be able to have the camera on, recording a video of the entire descent. So the image you're seeing right here this is one of the first frames of the video. This is actually the heat shield itself as it just detached and is just going to fall to the surface of Mars. And again, we're still, tens of kilometers up here. You can see right here, there's some dark colored dunes and some other details in here. I won't show the entire descent video itself just for the sake of time, but you can certainly see it. If you go to YouTube, you can just look for MARDI descent video, and it'll show up. There's a lot of really good versions out there. A lot of people processed it, made it into a very, very interesting video. But in the end, the descent video came out great, and a lot of the engineers, right after we landed, I was talking to them at JPL, and they said that the video itself, it really added a whole new dimension to being able to look at the actual landing system, because you could certainly really read the telemetry from the rover, but getting to visually see it really added a whole different dimension to it. And the landing ended up working great with that sky crane maneuver. So JPL actually stuck with that for the Perseverance rover that landed, again, a couple months ago. So now, with that being said, having this MARDI camera, once we land on the ground, it's only a couple feet off the ground. You might be thinking, well, what's the point of having the camera there now? It did what it did, during landing, but we've actually found some pretty interesting uses throughout the years. So I'll show you this right here. These are actually little animated 2 frames. You could actually see right here in the top left corner, you can see the wheel itself of the rover. What we'll a lot of times do is when we drive to a new area, we'll take one of the MARDI images, just kind of as a documentation to show where we are. And you can see clearly the image itself shows up very well, lots of detail in it. And what we a lot of times do is if we're sitting in an area for weeks or even potentially a month or so on end, we'll actually take a series of images throughout that whole time. And you can see in particular, this one was over the course of just one day, January 23rd to January 24th of 2017. And you could see just how much wind movement there is that's blowing those little, little dunes around it there. And you could see clearly how much the wind distorts the wheel tracks as we went through. So again, it's ways to find really interesting science that you could get out of an instrument that its primary purpose was just 7 minutes during landing. Also interesting what we do, and I don't have one to share right now, unfortunately, but again, you could search online. We do what we call our MARDI sidewalk videos. And what we do with those is we'll actually turn the MARDI camera on and take a video while we're driving. And those are really interesting because getting those series of frames throughout the whole drive, you could actually create what's called DEMs, digital elevation models from those frames, because we know exactly how far apart they are. And we could see, like in this case, the dunes right there, we could get an idea for how tall they are just based entirely on those 2 frames right there by creating, what's really called stereo imaging. So again, easy ways to get some really interesting science out of, again, a camera that was only meant for one purpose when we very first landed. So MARDI's been great. I've enjoyed getting to see just the images it brings back. But with that being said, we will, we'll move on here. Oops, stand by just 1 second. I think I lost my connection. There we go. Okay, PowerPoint issues. Anyways, moving on, we'll move on to the Mastcam images. Now, Mastcam is certainly one of the more, how do you want to say, workhorse cameras, if you will, of the rover. And I had mentioned earlier in that first image, we had 2. There's the 34 millimeter and 100 millimeter cameras. Now, the reason why we have 2 different ones is basically what those different numbers there mean is, think of it as the zoom level of the camera itself. The 34 millimeter camera is similar to what you would see in a typical point and shoot camera where you're not zoomed in at all. It's just the initial zoom rate. However, the 100 millimeter camera is going to be as you're zoomed out much further. So I want you to kind of focus all right here in the image, kind of on the middle off to the side a little bit. You can see this rock right there. There's a little rocks right there in the outcrop. And I'm going to jump back and forth between these 2 images. So that first one was the 34 millimeter. Here's the 100 millimeter. So now all of a sudden you can see this rock, these rocks in the front and this outcrop much larger. I'll jump back and forth between the 2. So now these 2 images were acquired at the exact same location at the exact same time of day. They're only about a second or so apart. And you could see how much further into the distance we're able to see with this 100 millimeter camera than we can with the 34 millimeter camera. Now, there's a number of reasons for us to have this. One of the big ones certainly is, when you're driving a spacecraft on another planet, you really do want to kind of conserve as much as you can on wear and tear of the vehicle. The more you drive it, the more degradation you're going to get. So in this case, when we have the 34 millimeter camera, you could use that for good contextual idea of what's in the area. And then if any of the science team says, oh, this is pretty interesting over here, this rock outcrop is pretty interesting. Is this something we want to drive up to? We can't really see it too well. So with the 100 millimeter camera, you're able to just stay exactly where you are, don't have to drive, All you got to do is point the camera and then just acquire the image in 100 millimeter, and you could see how much more detail we could get just with that one camera right there. Now, in this case right here, there wasn't anything in particular that we decided was nothing in particular that we decided we would need to drive up to this rock outcrop for. But again, that just shows one of the many uses that the Mastcam, the two different Mastcams could have. So again, I'll flip back and forth just a little bit here so you can see. Now, moving on, with that being said, Mastcam is an extremely versatile camera in the sense that it could take more than just those in-depth images. This right here is actually a little outcrop right at the foot of the rover, maybe 6-7 feet in front of the base of the rover. And there's a couple things I want to show about this image. First off, it's to show how well we could see with those Mastcams up close in front of the rover like this. We'll do these images after we do a large drive or a long drive, so we could see exactly what's in front of the rover, so that we could then take out the arm and see what we want to conduct some science on. And this again shows us in very, very crisp detail everything that's in front of us. And then also the other thing to make note is you'll notice kind of these jagged edges kind of on the top and bottom. This is actually not one single image, but is actually composed of about 6 separate images that we then stitch together, and we call a mosaic. So the image is really, this right here, there's another image right here, another image right here, and then move down, we get another there, and then another there. And the idea behind this is you could get a very large high-resolution image from just the single camera. Now, each one of our single images we take are about 1,600 pixels wide by about 1,200 pixels tall. So you put 3 of those together, all of a sudden you have an image that's over 4,000 pixels wide by 24, it could be 2,500 pixels tall. So you get a very large, high-resolution image out of a camera that's able to take single pictures or single images at a quote-unquote much lower resolution, if you will. So again, this goes to show what we're able to do with the Mastcams. Now, one of the really cool things is we could also see actually very up close to the surface, and then every now and then we find something we're not expecting. This image right here is both showing how we could get up very close to the surface with just the Mastcams, but also some of the fun things we find totally by accident. This right here is actually a meteorite that we saw on the ground. We obviously weren't expecting to find it. They're pretty small. This one, if memory serves me correctly, I think this one is maybe 3-4 centimeters wide, maybe a little larger. So not very big. But again, you could see with the Mastcams, not only see it very up close on the ground, but you actually see quite a bit of detail in something that's not very large at all. Something that's certainly about the size of, at the largest, maybe a tennis ball, if not smaller. So again, a very high detail with just that one single camera. Now, certainly jumping in the other direction, Mastcam is also known for its very nice, large kind of panoramas, if you will, sweeping vistas. So this one right here, again, is a mosaic. You can see the kind of the more jagged edges like that. This one I think is about 8 images put together, and I really like showing this one because it shows with just that one single camera what you could do. Seeing up close right here, this is actually some of the rover hardware itself. You can see it goes off a little bit in the distance. There's this first little rock outcrop sticking right there. Go a little further back, you get a much larger one, and then keep going further back in the images, and you can see all the way to the edge of this rim right here, with lots of dunes, lots of detail right here in the foreground, in the distance. Again, all of which is in focus, going all the way into the back. So again, a very versatile camera that's able to do quite a lot with just some kind of clever ways of commanding it. And then lastly with Mastcam, one of the really cool things we do are what's called our 360s. Now this is quite literally a 360-degree panoramic. This left edge right here actually matches up with the right edge over there. So if you're able to take this and wrap it a full 360 degrees around, that would actually show you everything that the rover sees around it. So again, you can see in the front here, there's some rover hardware right there. Going all the way back, you can see nice detail. All the way into the very back, you can actually see a mountain sticking up right here. This is actually, the mountain is called Mount Sharp. This is actually the mountain that's in the very center of the crater that we landed in, called Gale Crater. So again, a very versatile camera. This one, I believe, this has got to be probably at least maybe 6, 7, 8 rows tall. There's a lot of images that make up this mosaic. So you're talking tens of thousands of pixels across here that we're able to do just with this one single camera system. And then just to end Mastcam, in addition to doing our nice, beautiful daylight images, we're also able to acquire images in the evenings. This is actually a Martian sunset acquired with the Mastcams. This is only a handful of frames, but you can see the sun is going down behind the edge of the rim right there, behind that mountain. I always like to just to end Mastcam's discussion just with this image. Very, very nice. This one was one we had planned out for a little while, trying to make sure we were going to get it right, and in the end, I think it came out beautiful. Just getting to see the nice Martian sunset. So jumping in to the next camera, this is MAHLI. This is the Mars hand lens imager. Again, this is the one that we decided to basically make because it was the same idea as a geologist with their hand lens. What we do as geologists is, when we have a hand lens, the idea is you could see very close to the surface of a rock. You could see crystalline structure, grain size, things like that, and get an idea for what the composition of the rock is. Now, MAHLI could do the same thing. It could get quite literally a matter of centimeters from the surface of a rock, from the face of a rock, and see very high up close. Again, grain size, structure of the rock, things like that. This image right here is actually not even as close as we can get. You get a little idea for size here. You can see some dust right here and some smaller pebbles. I believe this one was taken at a standoff of probably about 25 centimeters from the rock. So again, we could get much closer with MAHLI than we certainly can with the Mastcams. In addition to getting great science with MAHLI, we also actually use it for some engineering data. Now, these are actually two MAHLI images we took of the rover's wheels. We use these every so often just to monitor the wear and tear on the wheels. You can see we got a little bit of a hole starting right there. The wheels themselves are holding up pretty well, and again, we're able to determine this just by imaging them with the MAHLI camera. So again, in addition to being able to view images of a rock up very, very close, again from a matter of centimeters, we could also get these much further images that are much further away. Given another idea for scale, this wheel is actually about 15 inches in diameter. So that'll let you really again see how well the MAHLI camera can do this. So now, as you might be thinking in the back of your head, it's like, well, if you get up really close to a rock with the camera, that's great. But what happens if you get so close that you kind of start blocking the light around it and it's in shadow? So in order to mitigate that, one of the things we did is we put some LEDs on the rover, or rather on the camera. The idea behind this is it works just like the flash on a camera. When you take an image in low light, the flash will turn on and just briefly illuminate the scene really quickly. This right here is actually a Mastcam image of MAHLI as it's imaging one of our drill holes we did a number of years ago. This is in the middle of the night, so it's on Mars. Obviously, there's no light pollution, so it's as dark as you can get. And with just these LEDs turned on right here, you could see how well those LEDs are able to illuminate the surface for us with MAHLI. Now, this right here is an actual image that we did acquire with MAHLI with the LEDs turned on. This one we took, it was kind of interesting. We drove over this rock and actually broke off a little bit of the side of the rock right there. And we realized this was a good example to be able to use the LEDs to show it at night. So again, this image was taken middle of the night, and we've got the camera, a matter of centimeters off the surface of the rock, off the surface of the ground at the rock, and you can clearly see again how well the whole area is illuminated here. There's no sunlight whatsoever, so this shows really what we're able to do with those LEDs. Now, with that being said, some other things we can do, we realize with those LEDs is if we got the regular, white colored LEDs, why not also add an ultraviolet LED? So this is the exact same rock with taken a couple of matter of seconds later with the ultraviolet LEDs. Now, as geologists, one of the things you can do to help you determine the composition of a rock or what it's composed of is some minerals will actually fluoresce under a black light, under ultraviolet light. So the idea was we already had those white LEDs on the camera. Let's also install the ultraviolet LEDs to help us determine what the rocks are. It won't necessarily tell you exactly what it is, but it'll help you certainly narrow down what you're looking at specifically. So in this particular case, the rock actually, this lighter area, I'll jump back and forth again here. This light area that we were wondering about, it actually did not really fluoresce in the end, and that's certainly not a bad thing. It just again tells us or it gives us an idea of what the rock could be composed of. And then finally, with MAHLI, as I'm sure you've seen many times, we have a really cool ability to be able to quite literally take a selfie. It is very similar to what we would do here on Earth. You just hold your camera out with your arm, point it back at you, and take an image. Now, with MAHLI, it's a little bit different. Now, one of the very first things you probably notice is you can't see the arm of the rover in here at all. Why is that? So this is slightly different than a selfie with your cell phone, for example. It's actually not one image, but this is actually made of numerous images. I think there's about 60 some odd images that make this up. So just like the Mastcam mosaics, we do the same thing. We take a MAHLI mosaic. So we have an image here, have another one right here, another one here, and you just keep on going down through the rows until you get to about the middle point, right where the arm itself would start to be in the way of the images. At that point, we're actually able to take the arm and the camera, flip them upside down so that they're out of the way, and then continue imaging down, going through the rows until you get to the very end. And then finally, since we know the positions of everything, in particular the arm, we're able to stitch all the images together and very nicely and almost seamlessly remove the whole arm itself. Now, if you did see this image, if you looked at it at full resolution, full scale, you would see a little bit of seams right there in the middle, but not very much. So that's really how we actually acquire the selfies. And one of the fun things we always like to do with the selfies is, because we certainly don't acquire them all the time because it's a lot of bandwidth to be able to downlink that many images. One of the things we do is we'll do them after we have a long campaign in a particular area. We're performing a lot of science in a given area. So you can see kind of right here in amongst the red rocks of Mars, you could see a little bit of these gray rocks. So this one right here is a drill hole. We did some other science and some rocks here. I don't remember if there's any other drills in this particular selfie, but again, we do this just because it gives us an idea for a contextual idea for where we were and what we were doing at that particular time. So he's always been very good outreach images, and I love getting to show the selfies. And we do them. It is kind of it does vary when we do them. It just really depends on how long we stay in a particular area for. So that being said, we'll jump into the Perseverance rover. Now, Perseverance landed about 2 months ago. This is on February 18th, and Malin had a couple cameras on this one as well. So we have, similar to what we have on MSL, we have two Mastcam Z cameras, we call them now. The difference with these compared to the MSL cameras are these actually have a zoom feature. So unlike the MSL cameras, which are basically a fixed rate of 34 and 100 millimeters, the Mastcam Zs could actually zoom, I believe it's anywhere from 24 or 26 millimeters all the way up to about 110 millimeters, both of them independently. So this allows us to have more versatile dynamic zooming as we're looking at the surface of Mars. In addition, we also have kind of the equivalent of the MAHLI camera on the end of the arm. There's what's called the Sherlock system, which is composed of a few instruments. The ones we built and provided hardware for were ACI and then Watson. Watson itself is really the exact same thing as MAHLI, if you will. It's a visible color spectrum camera that, again, can get very close to the surface of the rock, and actually the specific camera that I work on for Perseverance itself. Now, show you a couple images. Now, we are certainly only, like I said, only about 2 months into the mission. There isn't, we certainly don't have nearly as large of a catalog of science data as MSL. We're just really starting out, but this is one of the Mastcam images. You could see, again, just as versatile as the MSL cameras. You could see very good detail up close here, going all the way out to this very large outcrop, and then going to a larger rock wall in the background. Really excited to see what we're going to be able to do with the Mastcam Zs, just because they have that much more functionality now, even than the MSL Mastcams.
Is the background, that wall in the back, actually part of Jezreel crater? That the lip of the crater at all, or
if memory serves me correctly, where this image is taken, yes, I believe that's the edge of the. You're seeing the edge of the wall there. If memory serves me correctly on this particular image itself.
Great, thanks. Sorry.
But no worries. Yeah. So, and then with that being said, we all know about Ingenuity. The helicopter just had its first successful flight earlier this week. Again, this is a Mastcam image. I'd just like to show, looking up close at the base of the rover, showing the helicopter after it was deployed. You can see our tracks right there, wheel tracks right there, right along the edge. So again, you're able to see how high resolution we're able to get with the two Mastcam Zs that we'll have. So I'm really excited to see what they're going to be able to do. And then, of course, admittedly, my personal favorite, because it's the one I work directly on, is the Watson camera. Now, this one, again, is a mosaic. You can kind of see the slightly jagged edge right there on the top. And just like with MAHLI on MSL, we also we're going to be using Watson for some, engineering related things. So this is actually the Ingenuity helicopter itself. It was originally mounted on the underbelly of the rover and deployed that way. So we lowered the arm, turned on the Watson camera, and were able to take a series of images, a mosaic again, if you will, of the whole base of the rover as the helicopter itself was first deployed. So again, it's going to be a very interesting mission. We're only about 2 months in. I'm really excited to see what we're going to be able to do with everything we did with MSL in the past 8.5 years. We're going to certainly be able to do just as much science with Perseverance as we were with Curiosity, and I'm really excited to be able to be part of it, and really looking forward to seeing what we're going to be able to do going forward in the coming months and years. So, lastly is the Juno mission to Jupiter that I mentioned. We're going a little further out in the solar system now, going all the way to Jupiter. Now, we have a camera, as I said, on this one called the JunoCam. And there's some interesting technical challenges, engineering challenges that are presented with the Juno spacecraft. The interesting thing with Juno is it actually rotates on its axis. So these solar arrays, they're continuously rotating at about 2 RPMs, 2 revolutions per minute. And the thing is, JunoCam is mounted in between, pointed outwards. So really what that means is the lens of the camera is only pointed at the planet for, however many seconds out of that 2 RPM spin as we're going around. And again, as I said, it posed a lot of interesting engineering challenges. One of which was, as you know, if you take a picture with your cell phone, point and shoot camera, whatever, and you move your arms right as you're taking the picture, you're going to get blur across the screen, which is exactly what's going on here. The spacecraft is rotating as the camera is acquiring the image. So if we didn't do anything, we would just get a blurry image. So the way we're able to compensate for that and mitigate for that is what's called time-delayed integration, or TDI. And I'll get a little bit technical on you here. What that basically means is the sensor on the camera, it's a CCD. The sensor itself basically says after X amount of milliseconds, whatever TDI setting we have it at, after X amount of milliseconds, you're going to take the charge at 1 pixel and then shift it up to the next pixel above it. And the idea there is, since you're shifting that charge based on however much time you're calculating, you're able to basically take a clear, crisp image, because the sensor is technically the pixels that are being read on the sensor are technically pointed at the same point of the planet throughout that whole spin. And you're able to do that until you complete a full swath along the planet. Now, I will say the whole idea of TDI is complicated. It took me literally about a month to just think about it and really understand how it was working before I finally really got it. So don't feel bad if that description was a little kind of confusing right there, because like I said, it took me quite a while to really understand it as well. But it does work very perfectly in the images itself.
Another question for you, Daniel. Sorry,
yes.
I realized that the image of Juno itself is I'm assuming is just a CGI, as it were, but the image of Jupiter behind it, that was taken by the JunoCam?
So the image of Jupiter behind it, I believe this one was actually originally just an Earth-based image.
Oh, okay. Right.
Yeah, I think this one was actually even created before we got to Jupiter. Okay. But yeah, so this is just a CGI planet even in the back.
What I was going to ask was in the upper left-hand corner, that brightness. I'm wondering if that is maybe some aurora.
Yeah, so it's representing the aurora. That is one of the things that we have studied actually with the spacecraft, a couple of different instruments there. Right, so yeah, that was again one of the draws with the spacecraft itself. So moving ahead here, I want to show you all a really cool video here. So as we were coming into the planet, before we were entering what's called the Jupiter orbital insertion, we decided to turn the camera on actually and start taking images. So if you're familiar with the story of Galileo Galilei, he looked through his telescope and was looking at Jupiter, and he realized that there's these little dots around the planet. And after he'd watched them for a period of time, he had started to theorize that those are actually moons orbiting Jupiter itself, which is what ultimately led him to say that Earth is not the center of the solar system. We all revolve around the sun. Jupiter has its own little system of planetary bodies orbiting around it. So what we did is we turned the JunoCam on as we were coming into the planet, and literally filmed a movie. So this is quite literally what Galileo would have seen through his telescope. All these little dots are the different Galilean satellites. They are, I believe, in order: Io, Europa, Ganymede, and Callisto, and they're just orbiting the planet as it goes. We took this over the course of a number of days. Because while the moons are orbiting fast, they certainly do take a while to do a complete orbit around. I think we took one image every half hour in order to complete this over the course of a couple of days.
It's interesting. You can actually see them go into eclipse.
Yes, yeah, and if you actually follow some of them there, right on the left side, you'll actually see they kind of disappear there for a second, right as they're going behind the planet itself, because the sunlight's coming in from the right there. So pretty interesting video. Again, we did it purely for the public outreach aspect of things. Great video. I'll play it again here, and it's really fun because as you watch it, you see the planet is gradually getting larger, so you can see us as we're coming into the planet. Now, with that being said, that is one thing I wanted to mention about this spacecraft. So Juno is not in a polar orbit around the planet, or excuse me, it's in a polar orbit around the planet, but it's not in a circular orbit around the planet. We are actually in a highly elliptical orbit. And there's a number of reasons for this. Jupiter itself has a very high radiation environment. So if you had the spacecraft in circular orbit constantly being bathed in that radiation, it's going to eventually degrade and destroy the electronics. So one of the many reasons why we did the highly elliptical orbit is basically to allow us to not have to be continuously bathed in the radiation. So we come in, we use Jupiter right here as the example. Spacecraft comes in very far away, gets in very close to the equator, about 4,000 or so kilometers, give or take, and then it jets out really quickly and then goes really far out. Takes actually about 53.5 days to go all the way out and then come back again to get to the equator, or perigove as we call it. So they're about these 53.5-day highly elliptical orbits like that. And again, it's to help us just for many reasons, one of which is to help us avoid a lot of that radiation that we hit. There are other instruments on board that are monitoring its Jupiter's magnetic field, the gravitational pull of the planet. So they as well need to operate by going really close in and very far out like that. So that in and of itself has posed some interesting technical challenges, but it also actually made it a lot easier for us to do, because we're only planning sequences that acquire these images once every about 1.5 to 2 months or so. So it's actually made it a lot easier for us to be able to downlink all the data we acquire as we're very close to the planet, and then just send it all back as we're getting really far out here. And then we start our planning cycle again, make sure we got everything right, gives us plenty of time. And then right as we get back into the planet, we're good to go again. And I should say, to get from pole to pole on the planet takes around 2 hours or so. So the spacecraft is moving very quickly around there. So with that being said, I'm sure you all want to see some of the images of Jupiter itself that we've acquired. So this is looking at Jupiter's North Pole. I will say hold off for just a second on seeing this scallop right here. I'll explain what's going on with that in a little bit. But one of the cool things about being in a polar orbit, like I said, is we've never been able to see Jupiter's north and south poles, because if you look at it from here on Earth, you're only looking at the equator, right along the sides of the planet, because all the planets in the solar system orbit, roughly on the same plane as one another. So you could really only see them directly from the sides. And we've never had a spacecraft at Jupiter that is in a polar orbit looking at the poles. So coming into the planet, we didn't really know exactly what to expect at the poles. We had a little bit of an idea because the Cassini mission at Saturn was able to image the poles, but we didn't really have anything in Jupiter, so we only had some kind of ideas of what it was going to look like. In the end, once we got there, you could see it's a very highly chaotic environment. You see some cyclones spinning around there. Other things you see there's storms, but they're not even really cyclonic. They're just moving all over the place. The cloud tops are constantly moving. An extremely chaotic and very interesting environment that we really not everybody expected to see. So it was very interesting to see those very first few images that came back right as we got over top of the planet. And then certainly as you go on further down into the lower latitudes, you can see a lot of the banding along the planet, which again is a very chaotic environment itself, even along the bandings. So it's very, very interesting planet to work on so far, and certainly different for me. Again, coming from a geologist point of view, Jupiter being a gas giant. I don't have a degree in meteorology, for example, so someone with that knowledge would certainly be able to understand what's going on a lot better. But I've certainly enjoyed getting to watch or getting to see all the images that we've gotten back so far. So that being said, what do the images themselves look like? Now, I had mentioned earlier that this is a little bit different than kind of the point-and-shoot camera style that we have for the rovers. Now, since the spacecraft is spinning and we're using TDI, like I mentioned, we actually get these images back that what we call, these are the Venetian blind images. Now, zoom in here. Now, each one of these are the individual red, green, and blue framelets. They're all about 128 pixels tall, and as the spacecraft is spinning, we're acquiring just these short 128 pixel tall framelets in each of the 3 frames simultaneously. And then once we get to that end of that 128 pixels, we then repeat again and then continue on the way down until you get a full swath of the planet like that. And then from there, we do have to do some processing, certainly here on the ground, in order to put them together. But since we know exactly where the spacecraft is at any given moment, its orientation, we know exactly where the camera's pointed, the speed it's going, we're able to take all that and then stitch them together in a nice, perfect, seamless image right here. So this image right here is this image right here. These two are the same thing. So you can see how we're able to just take all that data we have from the spacecraft of where it's pointed, as well as where all the different framelets are within the image, and then stitch them together to make a nice image right here. And this is actually looking, just for informational purposes, this is looking at the South Pole. So again, kind of just like the North Pole up above, you can see this kind of crazy chaotic terrain right there. Or not terrain rather, but crazy chaotic cloud tops, I should say, going all throughout the South Pole, and then again getting up into the banding. Now I'll jump back here to that first image. Now I did have this scallop right here in the side of the image. Now the reason behind that is we've been at Jupiter now since 2016, July of 2016, and the orientation of our orbiter has changed slightly as the orbit progresses. So we're technically really not pointed directly at the planet right now, so that, or what's called nadir pointing. We're actually pointed a little bit off to the side. So the reason why we've got this, kind of cut in the side of the image is because as we're going, the camera's pointed more, off to this side of the planet. So this front edge right there is actually kind of clipped off. It's out of the field of view of the planet itself. So that way, when we go to stitch the image together, if we've got this little, kind of clip off right there on the side of the image, we don't have that little bit of data. Now, this is expected. We certainly knew this was going to happen as the mission went on, and it actually is already starting to get better. We're starting to kind of come around, a full, 360 here. So we're starting to actually get into a better orientation on the planet again. So we certainly will be back to where we were, with this image right here, and we'll certainly start getting some more nice full images of the planet itself. So now, with that being said, what would a little talk about Jupiter be without mentioning the Great Red Spot? Everybody knows Jupiter's Great Red Spot. It's kind of its defining feature. A couple of years ago, we were really lucky enough to have an opportunity where we were flying directly over top of the red spot. So we took a series of images with JunoCam and got some beautiful images of the red spot itself. I'll go forward here a little bit. Again, the red spot itself is so big it actually can't even fit within the field of view of the camera itself. So you can see it's clipped off here just because it's so large. But again, you can look at this image right here. You see it's kind of spinning in a counterclockwise orientation, and then even within that, you can see there's a lot of chaotic turbulence going on within the red spot. Very interesting storm. Now, one of the interesting things about the red spot is it's actually shrinking, believe it or not. We don't know exactly why it's shrinking. We don't know if it's going to continue to shrink, if it's finally going to stop and stagnate. Maybe it'll disappear at some point, but it has gotten noticeably smaller. When I was younger, in the 90s, we would always get to say, you could fit 3 Earths side by side within the red spot. And it's actually shrunk enough where you can not only fit about 2 Earths within the side by side within the red spot. So it definitely has gotten smaller. It's pretty interesting when I look at some of those older images from, 70s, 80s, and the 90s, that even that people have taken just from their backyards with their telescopes. When I look at those compared to a lot of the images we're seeing of the red spot from JunoCam, you could clearly see the red spot's not nearly as wide anymore. It used to be much more elliptical. This one, it's getting a lot more circular. I'll go back to this first one. It's getting a little bit more circular, not as wide as it used to be. So we'll certainly continue to monitor it ourselves while we're there. All the cloud tops on Jupiter are moving, including the red spot itself. So we certainly don't have the ability to, always know exactly where it's going to be. You could only predict, but we'll certainly continue to image it while we can. We've certainly gotten a lot more images since in the past couple of years, and we'll certainly see what happens with the red spot itself. So, but it's pretty interesting to see that hopefully Jupiter's defining feature is not going to disappear, but only time will tell on that one. So with that, we're starting to get towards the end here. So I just wanted to say thank you all very much for having me, and just put up these few URLs. All the images we acquire on any of our spacecraft, these are all public domain. These are all the URLs for the 3 separate missions, where you can get their images, process them, do whatever you want. Juno's really fun, certainly, because we have the website set up kind of as a public outreach place specifically. You could download the images, process them, do whatever you want, and actually re-upload them directly to the website and get to share with the public. We've got lots of submissions on it throughout the years, so definitely encourage you to jump onto any of the websites, see what we get. Images appear, certainly for MSL and 2020, the images appear pretty much right when we're getting them down, and then Juno, we attach them right when we get them down as well. But again, since we're in the highly elliptical orbit, you pretty much get a whole bunch of images within the course of about a week, and then we have the next number of weeks off as we're planning, as the spacecraft is getting further away from the planet and then looping back around again. So with that, again, just wanted to say thank you all very much, and I think we got about 10 or so minutes here for questions. So with that, I'll stop sharing, and let's go into some questions.
Outstanding. Outstanding. We do have a couple of questions here. Denise asks, how do you keep the lenses clean to take such clear and great photos?
That's a good question. So it's kind of different for all of them. For MAHLI and Watson on Curiosity and Perseverance, we actually have a cover that does close right over top of the lens itself. With Mastcam, those are up very high, and they're very very vertical shields kind of in front of the lenses themselves. So we really don't get a high dust buildup on those. MARDI on Curiosity was a different story. Again, since that one was really only meant to be a single-use camera, we didn't have anything. That camera's just bare. The lens, it's there, and we did acquire a bit of dust on it. With a lot of the images that we take, they still have dust from landing on them. So there actually is a little bit of contrast stretching and processing will apply to the images just to make them a bit more crisp and clear. But so by and large, that's pretty much what it is. We got a cover on the one, and then just the vertical lenses right there, and that's about really all you could safely do.
All right. Again, Copernic being Copernic, we always draw some of the techies, and so David asks, can you go into a little bit of detail of the camera sensors and their capabilities?
Yeah, so the sensors are, this is one of the things I always tell people at outreach events. So they are, for all intents and purposes, they're actually the same thing as anything you'd get from a camera here. It's just a 1600 by 1200 pixel CCD sensor. It is certainly a lot more durable than like a consumer camera. They're radiation hardened. They're able to withstand temperature changes much more. Like on Mars, for example, as I'm reviewing telemetry every day, I could see the temperature get down to, in the winter months, -70, -80 Celsius. So they get really cold, and then also gets pretty warm. So you need to have a sensor that's able to, withstand that. As well as like vibration of launch. You're launching on the top of a rocket. Atlas V for actually, I think all 3 missions were Atlas Vs. So you got a lot of vibration there. So the CCDs themselves really need to be able to withstand that. So in the end, technically, they are pretty much the same thing that you would get even in like your cell phones. They're the same idea as that, just much more durable for space exploration.
Right. And it appears that again, the fact that you can see information in UV, so it's a little wider than that our eyes would otherwise be able to see.
Yeah, admittedly I don't know the full spectrum that we could see with this particular CCD. I don't know off the top of my head. With that being said, there are actual technical papers out for all the instruments on any of the spacecraft. And they do actually have all those hard numbers in there. The whole spectrum that you can see, for example, they'll have like f-stops for the cameras, okay. all sorts of technical information like that in them.
Yeah. And are they auto-focusing, or do you have to manually focus, or?
So actually both. For the rovers, they're actually designed to be pretty much a point and shoot camera. We have the ability to do autofocus, which we use quite often, but there are times certainly when we do a manual focus as well for one reason or another. Yeah, so you could do both. And I admittedly couldn't tell you how often we use one over the other, but yeah, I mean functionally they do function the exact same as you would with a point and shoot camera.
All right. Maureen asks, how did you move from geology to camera development, or what is your job also at MAHLI?
Yeah. So for me, like I said, I've always been interested in space exploration, and the geology actually came about later. That wasn't until I was later in college. But I've always had a very strong technical background. I've always been, playing with computers, programming, playing with operating systems. I have a strong Unix background, things like that. So really the draw for me was after I had the geology and the space exploration, then I saw this job come up. I realized I could actually marry my 2 interests right there. I've got, the geology, the planetary geology, and then the computers and technical things right there. So really that's kind of how I came to be with that. It was just being able to marry the 2 interests right there in the single field.
All right. Douglas asks, what does the helicopter do during its other flights?
To be completely honest with you, so I actually don't work on the helicopter, so I don't know the specific plans for it yet. That one I honestly could not answer that one.
Now, it seems to me that at some point, Perseverance is going to move on and explore areas of Jezero. I think, isn't Ingenuity basically going to run its course and just sort of hang? It's not going to. It's not going to be taken anywhere, right?
Exactly. Yes. it does have an expected lifespan, just like any of the spacecraft do. I'm not sure what the numbers are off the top of my head, how long they're expecting it to last for, but So it's eventually gonna. The rover's obviously going to outlast the helicopter. Yeah. So. So we'll see what they're able to do, but so far they've been successful with everything. It's been pretty.
I heard they just had a successful second flight just recently. And,
just the other day. So.
Went up higher and stuff. Let's see here. Phil asks, can Watson take closer pictures than the SuperCam micro camera on the mast?
So technically, yes, just because we could get the camera up so close. I think the 2, once we get Watson back a little bit, I think we could get to similar resolution between the 2. But I think technically Watson actually can get closer than SuperCam can, I believe.
All right. Let's see here. You sort of answered that again. There's no infrared sensors per se on any of those missions.
Not on our cameras. There actually is an IR sensor on Juno. We didn't build that one specifically.
Right.
But there is an IR camera on that one.
Now I noticed on Perseverance you've got the Mastcam Z. You said you have two cameras. Can you actually do 3D imaging with that as well, or
so we actually even did that with Curiosity. You could do the stereo imaging, if you will, like that. We've done it before with Curiosity, and technically, we have the ability to do it with Perseverance as well. Nothing's been done yet, obviously, because we're so in the infancy with the mission. But yeah, so it certainly has the ability to do that.
Right. All right. I'm trying to think of that. I actually had another question. So, like, if we now go out to Juno, is there an expected lifespan of Juno? Like with Cassini, they eventually sort of ran out of fuel, station fuel, and said, okay, we are going to plow it into Saturn. What's the plan for Juno?
Yeah, Juno's actually going to be the same thing. In the end, we will deorbit, as we call it. That's the nicer way of saying it, because the spacecraft really does kind of become your baby. But yeah, so we eventually will deorbit into Jupiter, just the same as Cassini did with Saturn. So I don't know the specific date of that yet, but we got a little while to go. So
it's just we call it a rapid deassembly.
Yeah.
Exactly. I don't know if you could bring your presentation back up. I wanted to go back to, you had that picture of looking at Curiosity's wheels, and yes. I was going to point out something here if you could.
Let's see here.
Sorry, I realized you weren't planning on this, but
nope, no worries.
Yeah, there we go. Just those images right there, yeah.
There we go. Yes.
So we from time to time we've been fortunate that JPL has been able to, the outreach program has sent a sort of a engineering model of Curiosity's wheel, and and I point out those rectangular and square holes, and you know about those, right?
Yes, yeah. So there's two comments I'll make for it. The technical reason of having those holes was actually because of something they ran into with the Spirit and Opportunity rovers, where one of the wheels was actually punctured by a rock. But they had realized as they were driving, it was a nice way to kind of keep track of the wheels as they were going. You could see where that little hole was. So they purposely put those holes into Curiosity's wheels. With that being said, JPL being JPL, we are all nerds. Those holes specifically say JPL in Morse code. Yep. So that's the fun thing, yeah. So
yeah, I mean, it seems like actually that image looks like it's backwards, but if you're reading it, right to left or left to right, but
exactly, yeah. So yeah, exactly. If you're looking at it, depending on the
way the wheel is oriented, but yeah. So I was told somebody had said that JPL wanted to put this sort of a JPL sticker on the side of Curiosity, and NASA said no, you can't do that. So that some engineer came up with okay, well, we'll just tag Mars with JPL. Is it?
Cute little way to do it.
Yeah, absolutely. So, all right. Well, this has been fantastic. Some of those images I just have not seen, and I just to see it at such detail. It has to be so exciting and so rewarding to know that the work that you all put into this results in these just fantastic images, and then the science that comes out of that. People will be using that. I mean, obviously we're still learning what we did with the moon from 50 years ago, and I can only imagine that now with this technology, it's just allowing us to dive deeper into the formation of our universe and what's going on. So
yeah, it's definitely been a lot of fun. This really is my dream job. Like I was saying, I love getting to do this. So this is it's good to know that we're out there, we're still able to do this. And there's missions certainly in the planning stages right now that are going to be coming down the line as well. So it's a lot of fun to get to work on, and definitely rewarding.
Excellent. So one last question is, when was the last time you had a Speedy?
Well, I do actually get the marinade shipped to me. So
okay.
So last time I ordered some, it's probably been about 6 months since I've had one. But made in Binghamton, it's been a number of years.
Okay, all right, very good. Well, again, it was great to meet you, Daniel. I really appreciate it. Obviously, if you ever find a reason to be back in town, would love to have you up here again, and maybe do a presentation in person. If you're up for that. And I thank those that are watching on the live stream, and again next Friday at 7 o'clock will be a talk about trail cams and what we can learn from nature for those trail cams. There's some great images that we'll be able to see, and Rocket Fest is coming up, so check our website out for that. And if you get a child or a grandchild that you think might enjoy a Copernic summer camp, again, you'll have access to that on our website. So, Daniel, take care. Look forward to seeing more images from Perseverance and Juno and Curiosity as well. So, have a good evening.
Absolutely. Thank you all very much for having me. I appreciate it.
Take care.